All right. If something is rolling, then it has both rotational and translational motion. Okay, so it's spinning. La, 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 and roll. Oh, sorry, my bad. Just shoulder check. Okay, so it is both spinning rotationally and the whole thing is moving. The center of mass is moving as if it was a block translationally. Combine those together. Watch your shins. This goes pretty well. That was a good roll. Okay. Get both of those together. Okay. So, energy-wise, you have both rotational kinetic energy and translational kinetic energy. If something's rolling, center of mass is moving. Translational pieces of the mass are rotating around an axle. They all have the same rotational speed. So it's like, oh, rotational kinetic energy. Okay. Everybody good with the hoop? Okay, because it has the greatest moment of inertia. They're all rolling the same, so their translational kinetic energies are identical. But this one has a higher moment of inertia. All its mass is distributed away from the axis of rotation. All right, so quick review. Something's rolling down. So you have MGH initial, okay, and at the end we're going to make this ground zero. So initial final equals 1/2 mass times speed squared final plus 1/2 I omega squared final. Has both translational and rotational kinetic energy. You can, let's say the I is, I don't know, I can't remember, sphere mr squared, just making that up. I think that's right, maybe. And then we know that rotational speed is equal to, speed is equal to rotational speed times the radius. So I'm going to go mgh is equal to 1/2 mass times speed squared, final plus 1/2 2/5 m, m r squared times speed squared over radius squared. Just that.
Would the Rn moment of inertia be the same as this a solid object?
Yes. Same as what? Like this R and this R being the same?
Yeah.
Yeah. Because you're looking at, like, if you considered this as like a pulley that's unspinning, or like unwinding, then this speed is going to be equal to this speed here and that radius. So as something rolls, what you're looking at is technically this point here stays fixed, doesn't move, and the axis kind of rotates around that at that moment in time at this distance r. Okay. So that's a great question to think about. So here, mass goes away. R squareds go away. The math here, this goes to that, so you get 1/2 v squared plus 1/5 v squared is equal to gh. So that becomes 7/10, 10/7 gh square root equals the speed. Okay with that? It's a lot of algebra. Trust me. Maybe. Good? Okay. So, which shape is going to, I feel like I'm going to regret erasing that. Which shape is going to win? Thumbs up when you have a guess. Did you do this last year? What? Oh! It was a cool animation. I swear I had it. Come on. There it is. There it is. Boom. Sphere, cylinder, solid. Sorry, that the red's a shell, and then hoop. Okay. This is the moment of inertia, the coefficient of these things. This is 2/5. This is 1. This is 1/2. This is 3/5. Okay. So one way to describe this is this one has a lot of its kinetic energy captured by rotational kinetic energy because the moment of inertia is higher. Where this one, this one has the least amount of kinetic energy tied up into rotational, so it has a greater percentage going to translational kinetic energy. That's one way to describe that. Go with that? Okay.